So hi everyone, this is Joy, your instructor for microprocessor and interfacing. Today we are going to see the architecture of the microprocessor 8085. You can also say block diagram of 8085. So let's see. The chip that you are seeing on the screen is actually a microprocessor. Now if you see inside that chip, you will see there are billions of transistors which are connected to each other, and there are different blocks which are present in the microprocessor. Some portion is the arithmetic and logical unit, some portion is the register, and much more. But by seeing this picture, you are not going to get that which portion is which. So that is why when you purchase any microprocessor, you will get a reference manual. In that reference manual, you will find that how many blocks are there in the microprocessor, and you are also going to see a proper block diagram of the microprocessor. And let's see how the block diagram of the microprocessor 8085 looks like. So this is the block diagram of the microprocessor 8085. Now it seems very big and difficult, but trust me, it isn't that much. Let's divide this block diagram of the microprocessor into the different sections so that we can understand it clearly. The first section of the microprocessor 8085 is the register section. There are different registers present in the microprocessor 8085. You can see that the registers named W, Z, B, C, D, E, H, L are present. Now each register is having size of 8-bit. So if you want to store 8-bit of data, you can use the register B, C, D, E and H, L. You cannot use the register W and Z because those are temporary registers, and those registers can be only used by microprocessor itself. So user cannot access those registers. Now what if you want to store 16-bit of data? You can also store 16-bit of data, and to store 16-bit of data you can make register pair. So how to make register pair? You can make pair of register B and C. You can make pair of D and E and H and L. You cannot make register pair randomly. You can only make these fixed pairs which are provided in the reference manual. You can see below this register there is a stack pointer and the program counter. Now to understand the working of the stack pointer and the program counter, let's see one example. Now you can see the memory of the microprocessor. Now when you program the microprocessor, all the instructions will be stored from the starting location. So you can see that from the location 0 all the instructions are stored. Right now the program that we have created is of 6 instructions. So these all instructions are stored in the memory. After the instructions are stored in the memory, the processor will start doing its task. Now what is the task of the processor? The processor will fetch the instruction from the memory, it will decode the instruction, and it will execute the instruction. So to fetch the instruction from the memory, the processor should know that from which location it has to start the process of fetch, decode and execute. And to find the location, the processor gets help from the program counter. So you can see initially when you start the microprocessor, the value of the program counter will be 0. Now whenever processor wants to fetch any instruction, it will see the value in the program counter. So right now the value in the program counter is 0, so processor will fetch the instruction from the memory location 0. So processor will fetch that instruction, it will decode that instruction and execute that instruction. After the fetch process of the instruction 0 is done, the value of the program counter will be incremented. So you can see the value of the program counter is now 1. So when processor wants to read any instruction, it will see the value of the program counter. Right now the value of the program counter is 1. So processor will fetch the instruction from the memory location 1. after fetching the instruction, the value of the program counter will be incremented. The processor will decode the instruction 1 and it will execute, and next time it will fetch the instruction from which location? The memory location 3. Okay, so every time after fetching the instruction, the value of the program counter will be incremented, so that the next time, for the next time, processor can know that from which location it has to read the instruction. Now you can see that there is a stack pointer. You can see the value in the stack pointer is the 1 2 3 4. Now from the value of the stack pointer, you can know that at which location stack pointer is pointing, and that location, it is a top of the stack. So what is the top of the stack right now? It is a 1 2 3 4. This is it for the register section. Now we are going to see the next section, that is ALU and the flag section. You can see that there is a ALU. Now what is the function of ALU? ALU means the arithmetic and logical unit. You all know that using the ALU, processor can perform arithmetic operations such as addition, subtraction, multiplication, division. Using the same ALU, it can perform some logical operations too, such as AND, OR, XOR, etc. Right. Then after, the next block is the accumulator. Now the accumulator, it is a special purpose register. Whenever microprocessor performs any calculation, any arithmetic and logical operation, the answer will be stored in that accumulator. You can see that the accumulator is connected to the ALU. That is a one function of the accumulator. Accumulator can be also used to send and receive data outside of the microprocessor. So if you want to send any data outside of microprocessor, or if you want to receive any data from the outside of the microprocessor, accumulator can be used. The next register is the temporary register. Again, this register cannot be used by programmer, and temporary register, it is used by microprocessor to store any temporary data between any arithmetic or logical operation. After that, you can see there is a flag register. So as you can see that this is the pattern of the flag register. The size of the flag register is 8-bit, but total 8 flags are not present, only 5 flags are present. Which are these flags? There is a sign flag, then there is a 0 flag, auxiliary carry flag, parity flag, and the carry flag. Now let's see when this flag will be affected. So this is the example. We are performing the addition of these two 8-bit numbers. When you perform any arithmetic and logical operation, the value of the flag will be affected. So all flag will be affected when you perform any arithmetic and logical operation. Now let's add this number and you will get the answer. So let's name these bits from D0 to D7. Now for the sign flag, when after performing any arithmetic and logical operation, if the value of the D7 bit is 1, in that case the sign flag will be set. So you can see that the value of the sign flag is changed to 1. After performing any arithmetic and logical operation, if the value of the D7, or we can also say that the value of the MSB is 0, in that case the sign flag will be reset, means the value of the sign flag will be 0. After that, let's see when the 0 flag will be affected. So after performing any arithmetic and logical operation, if all the bits from the D0 to D7 is 0, in that case the 0 flag will be set, means the value of the 0 flag will be 1. Right now you can see that in the answer all the bits are not 0, so value of the 0 flag will be 0. That is, we can say reset. The next flag is the auxiliary flag. The function of the auxiliary flag that we are going to see by a different example. Let's first see how the parity flag is changed. So right now except that the value of the auxiliary flag is 0. After that, the next flag is the parity flag. Now when the parity flag will be set? After performing any arithmetic and logical operation, if in the answer total number of ones are even, in that case the parity flag will be set. So what if total number of ones are odd? In that case the parity flag will be reset. So you can see that the total number of ones are odd, so the parity flag will be 0. The last flag is the carry flag, and when the carry flag will be set? So when you are performing addition of, let's say, 8 bits and you are getting 9 bit in the answer. So we are getting 8 bit answer and the 9th bit is carry. So when the carry is generated in the D7 bit, in that case only the carry flag will be set. If we are getting carry apart from the D7 bit, in that case carry will not be set. So right now the carry flag will be reset because carry is not generated at D7 bit. Now let's see how the auxiliary carry is generated. Again, let's see the example of addition of this two 8 bits number, and after adding this number you will get this answer. Let's name these bits from D0 to D7. Now when this auxiliary carry will be set? So when you perform any arithmetic and logical operation, when the carry is transferred from D3 to D4, in that case the auxiliary carry will be set. We can also say that the carry is transferred from the lower nibble to higher nibble. What is the meaning of nibble? Group of 4 bits. So when you perform any arithmetic operation and the carry is transferred from lower nibble to higher nibble, in that case the auxiliary carry will be set. So you can see that the value of the auxiliary carry is 1. What is the value of the sign? What is the value of the sign flag? It will be 1 because the D7 bit is 1. What is the value of the 0 flag? It will be 0. Why? Because all the bits from D0 to D7 are not 0. What is the value of parity bit? So total number of ones are even, so parity flag will be set. And carry is not generated in the D7 bit, so value of the carry flag will be 0. Now let's see one more example, and for this example you have to find and you have to tell me that which flags will be affected when we perform this operation. Now let's move to the next section, that is the control unit. The first two pins in this block is the power supply. The first one is a plus 5 volt, it means that it is a VCC pin, power supply pin, and the next one is the ground, for the ground purpose of microprocessor. The next two pins of the this block is the X1 and X2. This pins is used to generate clock. Now processor, it works at particular frequency. The higher the frequency will be, the processor can work that quickly. So to function, processor needs clock, and we can provide clock to the microprocessor by using a crystal. You can see that the crystal, it is a device that is having two pins, and when you interface this crystal to these two pins, the first two pins that you can see are for the power supply. The first one is the plus 5 volt, which is also known as the VCC, and the next one is the ground, which is for the ground purpose of the microprocessor. The next pins are the X1 and X2. Using this pin, you can provide particular frequency, particular clock frequency to the microprocessor. Any microprocessor in the world requires frequency, clock frequency to operate. If you have heard somewhere your computer is having a microprocessor, it is working on a particular clock frequency, let's say 2 GHz, 3 GHz, like that. So every processor needs a clock frequency, and to provide the clock frequency we have to use the device which is known as crystal. Crystal is used to generate particular frequency. Now you can see that the crystal is having two pins. These two pins can be interfaced to the X1 and X2 pin, and processor will get some clock frequency. Now always remember, the operating frequency of the microprocessor is divided by 2 of the crystal frequency. You can see that if we provide crystal frequency of 4 MHz, the processor will operate at 2 MHz. If you provide frequency crystal of 6 MHz, processor will work as 3 MHz. So the internal frequency or the working frequency of the microprocessor, it is divided by 2 of the crystal frequency. Now this internal frequency is available at clock out pin. You can see that this pin is an output pin. It means that this pin can be connected to any peripheral device. And because the internal frequency is available at this pin, the peripheral device can synchronize itself with the microprocessor. So there can be no data loss. The next pin is the ready pin. The ready pin is the input pin. So when any peripheral device is ready, it will inform the microprocessor by sending signal at this particular pin. So when processor receives signal at this pin, it will understand that the peripheral device is ready for the communication. The next pin is the control pin, which is read bar, write bar, and the ALE. Notice these pins are the output pin, and bar means these pins are active low. Using this pin, processor can read or write the peripheral devices or the memory. The ALE pin is used to demultiplex address and data bus, and when we are going to discuss the demultiplexing of address and data bus, we are going to see that how the ALE pin functions. Right now we will only see the full form of the ALE pin, which is address latch enable. Now the next two pins are the status pin, which are S0, S1 and IO/M bar. You can see that these pins are the output pin. From the S0, S1 and the IO/M bar pin, we can understand that what are the process that is happening inside of microprocessor. So from the combination of S0, S1 and IO/M bar, from the status of this pin, we can understand that what process is happening in the microprocessor, and that you can see on the table. Then the next two pins are known as the DMA pins, which are the direct memory access pin. You can see that for the DMA, two pins are there, hold and HLDA. The hold pin is the input and the HLDA is the output. So when these pins are used, when any peripheral device wants access of the system bus, what is system bus? It is a combination of address, data and control bus. When any peripheral device wants access of the system bus, it will send request at the hold pin. When processor receives request at the hold pin, it can grant the request by sending the acknowledgement, which is HLDA. If processor is not sending any acknowledgement, so peripheral device is going to think that the processor is busy and it cannot provide the system bus right now. The next two pins are the reset pin. You can see that the reset in and reset out. Reset in bar is the input pin and reset out is the output pin. So if you want to reset the microprocessor, you can send active low signal at the reset in bar. Because bar means active low, if you want to use this pin, you have to send low signal at this particular pin. So when you send 0 signal at this pin, the processor will be reset. And when the processor will be reset, processor will provide the acknowledgement at the reset out pin. So if we are getting high signal at the reset out, user can understand the processor is reset successfully. So this is it for the control unit section. Now let's see the interrupt section. Before going to see the interrupt section, you should know first what is interrupt. So processor will be performing its own program, its own process. When processor is executing its own process and when the interrupt is received at the processor will stop that process it will hold that process and it will start executing the process which is initiated by the interrupt. After the process which is initiated by the interrupt is completed, the processor will start performing its own process from where it stopped, and that is known as interrupt. Generally, interrupt is divided into two types, which is hardware interrupt and the software interrupt. Right now you can see in the block diagram it is hardware interrupt. You can see in the interrupt section there are 6 pins. There is trap, then there is RST 7.5, RST 6.5, RST 5.5, INTR and INTA bar. So you can notice that from these 6 pins, 5 pins are input and 1 pin is output. So in the microprocessor 8085 there are 5 hardware interrupts, which is trap, RST 5.5, 6.5, 7.5 and INTR. The last pin, which is INTA bar, and it is for interrupt acknowledgement. Right, now let's see the priority of this interrupt. So you can see that from these 5 pins, the trap is having the highest priority and the INTR is having the lowest priority. So the priority, you can see that is a trap is at the highest priority. After that the RST 7.5, then RST 6.5 and RST 5.5, and last one is the INTR. So what is this meaning of priority? Priority means that if the processor is getting interrupt at 2 pins at the same time, so the processor will execute the interrupt which is having the highest priority. For example, processor is getting interrupt at its 2 pins, which is trap and RST 7.5. So it will execute which interrupt? The trap. Why? Because it is having the highest priority. You can see that the trap is non-maskable interrupt and the remaining interrupts are maskable. Now what is the meaning of the non-maskable and the maskable? Maskable means that if processor is performing very important program, in that case the processor can mask those interrupts which are less important or no important. But the trap is non-maskable interrupt. It means that if processor is performing any important program and if it is getting interrupt at trap pin, it has to stop that program and it has to execute the interrupt which is initiated by trap. Now let's see the next block, which is serial input output section. Using this serial input output section, the microprocessor can send data to peripheral devices. So the 2 pins are there in the serial input output section, which is SID and SOD. SID means that serially input data and SOD means that serially output data. It means that if you want to send data, for example, if you want to send 8 bits of data, in that case you have to send all these bits one by one. And if you want to receive any data, in that case you have to receive all the bits one by one. You cannot send data parallelly, right? Then after, the next block that we are going to discuss is the instruction decode section. You can see that for the instruction decode section there are 2 blocks. First one is instruction register, and after that there is a instruction decoder and the machine cycle encoder. Now to understand the function of this block, let's see one example. You can see that there is a memory, and in the memory one instruction is stored. Now you know the basic function of the microprocessor, right? When you start the microprocessor, it will start to fetch, decode and execute each and every instruction one by one. Right now there is only one instruction in the memory, so processor will fetch that instruction and When it fetch that instruction, the instruction will move from the memory to the instruction register. So the fetch process is completed. After the fetch process is completed, the instruction will be passed from the instruction register to the instruction decoder and the machine cycle encoder block. So in this block, the instruction will be decoded, and in this block, processor will know that how many machine cycles will be required to execute one instruction. You can consider machine cycle as a time required to execute instruction. So in this block, processor will get to know that how many time one particular instruction will be required to execute. Some instruction will require lesser time and some instruction will require more time. And after the instruction is decoded, after the processor knows that how many machine cycles is required, that decoded instruction will be passed to the control unit. The control unit is connected to different blocks within a microprocessor. So when the decoded instructions arrives at the control unit, the control unit will send different control signals. And by sending different control signals, different block within a microprocessor will perform some task, and together the instruction will be executed. So to fetch, decode and execute one instruction, these blocks are used. And this is it for the block diagram of the microprocessor 8085. And if you have any doubt, you can ask me in the comment section. Thank you so much.